Hi everyone. In this video we're going to look at a technique of integration called integration by parts. So when we've looked at integration by substitution, that's essentially reversing the chain rule from differentiation. Integration by parts is a reverse of the product rule. So if I look, I have here a statement of the product rule. The derivative of the product of two functions u and v is u times the derivative of v plus v times the derivative of u. So what I'm going to do is I'm going to take the integral of both sides. An integral can be distributed through an addition. So I'll take the integration of each part. Now, with respect to, say, x, or whatever variable the functions are being derived with respect to. So if I'm taking the antiderivative of the derivative of uv, well, that's just going to be uv. So what I've got here is uv equals u times dv plus the integral of u times dv plus the integral of v times du. So we usually write this as the integral of u dv equals uv minus the integral of v du. And we use it to convert an integral of a starting form that is a product of some function times the derivative of some other function to reorganize it, to arrange it. And it doesn't immediately look like that gets us anywhere because we still have an integral. But if that new integral is something that's easier to anti-derive, then we have actually gotten somewhere. So actually, there's a few situations where this works out really nicely. In the case, for example, where we have a product of an algebraic function and a transcendental function, and that algebraic function is not the derivative of some internal function, so in other words, we can't just do a substitution, then this is helpful. Or if we have the product of two different types of transcendental functions, so for example, natural log of x times the sine of x, integration by parts is going to be helpful. So let's look at an example where we have a product of an algebraic function, x, and a transcendental function, the sine of x. And I can't just do a u substitution because the derivative of the argument of sine, so in other words, if I just substituted u equals x, I'm not getting anywhere. I would just convert this into the integral of u times the sine of u du, and all I've done then is change the letter. I haven't actually made this easier to integrate. So what we're going to do is we're going to assign u and dv. So I'm going to pretend that this right here is the integral of u dv. Now u, I'm going to simply define in this case as x, and dv as the sine of x dx. Essentially, I'm assigning these such that I know the derivative of the thing that I turn into u, and I know the antiderivative of the thing that I call dv. So if u equals x, then du simply equals dx. And we're going to use the simplest antiderivative possible, because really any antiderivative would work, but we're going to use the simplest one. So if the derivative of v is sine x dx, then v has to be negative cos x. So now I have all the parts I need for my integration by parts. So remember, we said that the integral of u dv is equal to uv minus the integral of v du. So if I take all of these parts here and say, well, then that means that the integral of x sine x dx is equal to u, which is x, times v, which is negative cos x, and then minus the integral of v, which is negative cos x, so that's going to become plus the integral of cos x, times du, which is just dx. Well, now this new integral is actually quite a bit easier to deal with because I no longer have a product. So that's why it often is very handy if you have just a simple power type function, a polynomial type function, that can be u because it becomes simpler as we derive it. So now the antiderivative of cos x, well, is simply sine x, but now I do need the general antiderivative, so plus some constant. So the original integral that I was looking at was negative x cos x plus sine x plus some constant. And you could, of course, verify that this does reduce down to x sine x when you derive it. All right, so let's look at another. So again, we have an algebraic function being multiplied by a transcendental. My algebraic function in this case is x squared, so I'm going to let that be u. So u equals x squared because the derivative of that is very easy. Du equals 2x dx. And I'm going to let dv equal e to the x dx. Often we let our our transcendental function b dv because it's pretty easy to antiderive. So in this case, very easy because e to the power of x is its own derivative. So if dv equals e to the power of x dx, then v just equals e to the power of x. And now we put that into our integration by parts formula. So the original integral I'm looking at, which is the integral of u dv, so the original one, is equal to u times v, so x squared e to the power of x, minus the integral of v du. So that's 2x e to the power of x dx. Now, this doesn't really seem to have gotten anywhere because there's no substitution I can do here that's going to make this doable. But essentially all this means is that I have to do integration by parts again. Again, making u the algebraic part, and I'm going to ignore the 2 because that's just a coefficient. So I'll just put that out front. So u is going to be equal to x, and dv is equal to e to the power of x dx. So this time, du equals dx, and this time we will end up having an integral we can take. So v equals e to the power of x. Now, you might have to do integration by parts 2 or 3 times. In theory, if I had had something like x to the power of 30 e to the power of x, I would have to do integration by parts 30 times to get it all the way down. But we're not going to ask you to do anything quite that crazy. But it does work out nicely. So that means the integral I'm looking at is x squared e to the power of x minus 2, which I was just treating as a coefficient. Now that whole integral is going to be u times v, so x e to the power of x, minus the integral of v du, so just e to the power of x dx. And this one I can now finally integrate. So I'm not worrying about constants until I get to the very end. So this is x squared e to the power of x minus 2x e to the power of x plus 2e to the power of x, because the minus 2 times the minus e to the power of x, plus c. So there is the integral that I was looking for. And again, you can verify by deriving this that it does all simplify down, even though deriving it would require a couple applications of the power rule. It's kind of annoying, but it does eventually simplify all the way back to just x squared e to the power of x. All right, I'm going to look at one more example here. We'll do some examples in class of what happens if we have a transcendental times another transcendental. So in other words, the natural log of x times the sine of x. But I bring this one up because this is an instance in which the pattern I was using above doesn't really apply. So above I was using my u is going to be the algebraic part, and dv is going to be the transcendental part. But if I do this, I quickly run into trouble, not when I'm figuring out du, that's easy, 3x squared, but when I try to figure out v. We don't actually know the antiderivative of the natural log of x. So this is an instance where this pattern isn't actually useful. But I can reverse it because ln of x is something that derives into a nice algebraic expression. It's no longer transcendental. So if u equals ln of x, then du equals 1 over x dx. So in spite of the fact that means dv has to equal x cubed dx, which means that v is going to be of a higher power, and normally we would avoid making something a higher power. But in this case, that's going to work out okay because I no longer have a transcendental when I multiply v times du. So now if I put that into the format, the integral of x cubed ln of x dx equals, well, uv, so x to the power of 4 over 4 times the ln of x, minus the integral now of, well, v times du is x to the power of 4 over 4 times x is going to give me x cubed over 4 now. So x cubed over 4 dx. And this is now simply algebraic, so I can integrate that by using just the power rule. So I have x to the power of 4 over 4 times the natural log of x minus x to the power of 4 now over 16 plus some constant. And that is the integral that I was looking for.